Welcome everyone to our talk, Connecting the Dots, Let's Make a Game with Entities. I am Anna.
And my name is Daniel.
And we're both software engineers on the entities team within Dots. So today, let's make a game. Wow, great start. Let's make a game with entities. So we're going to start with a teeny tiny bit of theory on what is ECS and why are we using ECS, followed by the main part of our presentation, the fundamental concepts of ECS and the APIs that you're going to be using when you want to use ECS. And we're going to end with a small section on game objects and entities and how they interact with each other. So before you get nervous, this clicker is really doing a good job. Ah, there we go. Who is this for? Well, it's clearly not for people who know how to use clickers. It's for people who know C# and who know original Unity, not for people who know ECS. We're going to go from original Unity and build our way up to ECS. So at the end of this presentation, there we go, you have a toolkit on how to use ECS and how to start making your own game. So how are we actually going to do this? There's more than enough theoretical talks on ECS, so today we're going to take a bit more practical approach. We're going to explain ECS based on a game, more specifically, this game. We built this game, we chose something everyone can relate to. It's called Bugs versus Coders. You can see the C#, C, and the Java bugs entering the screen, and on the left-hand side, the brave developers and QA defending the homestead. Don't forget the coffee machine to keep them running. So while we go through this presentation, we're going to keep coming back to this example to make it a bit more visual. What is it we're actually talking about, and not just keep it theoretical, but practical. So unfortunately, we have to start with a tiny bit of theory. So ECS is fast. We've heard it many, many times, but why is it fast? ECS is fast because it follows hardware structure, which means we need to understand hardware structure. I promise I keep it as short as possible. So when the CPU wants data, it gets it from main memory. Getting data from main memory is slow, very, very slow. Imagine you're asked to write your name on a piece of paper, you forgot your pen, you have to walk like 20 minutes back to your hotel to get a pen just to write and sign your name in about 5 seconds. That is how slow it is for the CPU to wait for the data versus processing the data. Now imagine you had your backpack. Everyone has a backpack here. You can take a small subset of your stuff in the hotel with you here and access it. If you're looking for something, first look in your bag. Is it there? You don't have to wait. If it isn't there, you still have to wait and walk back to the hotel. That is called cache. When we're accessing, the CPU wants some data. It asks the cache, do you have my data? If it doesn't, unfortunately, we still have to wait. But if it's there, we can go immediately. Now, again, we get a cache line. What? We were just asking for a variable. Why are we getting all this other data? Data in memory and also in caches is stored in cache lines. It's generally 16 floats that are stored together and moved around together. So when we're asking for a single float, we actually get 16 of them, which is great because we can process all of them. And then we ask again, where's our memory? We get a new cache line. Unfortunately, between these, we have to wait. So while we're processing these, great job. We're getting there. At this point, we need a new cache line. There's actually something cool with, outside of this. It's called a prefetcher. The prefetcher, if it can predict where the next cache line is coming from, it can get it before we even ask for it, which means we're not waiting. Which means, well, I'm clearly asking for it, but there we go. Before we even ask for it, it gets the next cache line. We can immediately start processing. But keep in mind, prefetcher, if it knows where the next data is coming from, can already get it before we're even asking for it. And if we have the cache line, we can process more than one thing. Now look at the data structure of a game object. There we go. It's scattered throughout memory. If we're processing, let's say, blue data, we're hopping throughout memory, which means prefetcher has no idea where we're going to go next, cannot do anything. And once we get a cache line, chances are we can only use a fraction of the data that we actually get before we throw out the cache line and get a new one. ECS data is stored like this. For processing, we're stepping neatly and consecutively through memory, making sure that the prefetcher knows where we're going, and when we get the cache line, we can process all of it. So this is the data. How does this look in practice? We're going back to the example. By the way, if we're talking about bugs, obviously we're not talking about actual bugs, we're talking about the enemies in the game here. If we have these bugs, and we are processing the position based on the speed, we are processing the position and the damage in case we're attacking, and we are checking that the health doesn't fall below 0. So if these three pieces of memory are the game objects, and these are the actual data values that we're looking for. When we're doing the process, update position. Some operations take longer than others. There we go. We are jumping throughout memory. Hopefully. There we go. We're jumping throughout memory. Again, prefetcher doesn't know, data is scattered, cache lines are not utilized. We're doing the same thing in ECS with these neatly stacked arrays for each component. We're stepping through memory. It looks like this, neatly stepping through memory. But this is actually not even as efficient as it actually is. As I said, cache line, 16 floats. Transform, 3 floats. Speed, damage, health, each 1 float. This all fits within 1 cache line. So when we're stepping through this, 1 cache line, 1 cache line, 1 cache line. This is what it means when ECS is fast. We're leveraging the hardware structure and, in fact, the hardware peculiarities to store our data in such a way that the CPU can optimally get it and get access to it without having to wait for main memory to fetch it for us. So now we've talked a lot about data and how it's stored and everything, but ECS is 3 things: entity, component, system. If we go back 1 step and look at our game, these 3 bugs all have a position. How do we actually make ECS? Now we're going from back to mono behaviors. We have a simple mono behavior that simply updates the position based on the speed. If you move this to ECS, you split the data from the functionality. So the entity is the equivalent of the game object, if you will. The component is only the data, and the system is the functionality. So if we move this, data goes here, functionality goes there. We're going to explain how to use this later on, but for now, this is how you use it. The fun thing about this is that systems run based on what kind of components are on an entity. So in this case, the bugs are moved because they have the speed component, and the speed component is required for the system to run. This brings another fun thing, which is extensibility and flexibility. So we already saw we have a coder. Coder has a position, but we saw earlier it's not going anywhere, so it's not moving, doesn't need a speed. By simply not having the speed component, the system is not run, which means no functionality. The other way around, if it has a damage and a health, it can attack and it can die. If we take this 1 step further and we want to extend the game that you just saw, and say we want to have a bug that can explode, simply add a component and add a system. This way you instantly have functionality. You can add this radius to any entity you want, and because it matches the system's requirements, it will automatically run. This way you can prototype, you can change your game all throughout the thing, no problem. You've made it through the theory, now on to the fun point.
Yes, so now we'll go into some of the concepts of ECS. The first one, of course, being components, because it's crucial for us to have data on our entities. We saw one earlier, struct iComponent data. That's how we create a basic component that can store most of what we need. However, there are some problems. We also want to be able to store an array. And I'll go into an example now of why that can cause an issue. Because in our game, we want the ability to spawn bugs over time. We might create an entity that has a buffer that will store an array that it wants to spawn over time. So, certain entities, at which time in the frame do we want to spawn them? That's one big long array. There's just one problem. When we create this piece of code, we are creating what's known as a managed type. You guys don't need to know what a managed type is right now. What you need to know is that an array is a managed type. And so it means we're not allowed to use this because we're creating a struct iComponent data. Instead, what we have to do is we have to take this type that we want to create a buffer of and put it as what's known as an iBuffer element data. That means that now we're able to add this bug prefab as a buffer on our type, and so we can store an array of bug prefabs. So that's just two of the components. Now that we have the components, we of course want to see how we can use this entity data. Just having the component data isn't enough. We can create what's known as an iSystem or system base. We saw an iSystem earlier. You declare a partial struct implementing iSystem, and then there's this update loop. It runs every frame, and so you can get to implement some functionality that runs every frame. Now, I won't go into detail right now on what this code does, but it does move the screen box across the screen. We'll go back to that code later. But say you wanted a physics update. In MonoBehaviors, you can create an update function. You can create a fixed update that will update every fixed frame. You can even create a late update that happens at the end of rendering. Now, the code we just saw earlier, the move system runs every frame. So how do we then use the fixed update? Because on update is not really, it's only a fixed frame right now. An update. So a fixed frame, we put it in what's known as a system group. A system group defines when that on update should run. An on update is actually not run by default every frame, always run by every frame, but it's run here now, because we put it in the fixed step simulation system group, it can now be run every fixed update, so every physics tick. And if we wanted to put it in the presentation system group, then we can get it to run as often as a late update would, so at the end, just before rendering. There's even one for our default update. Now, writing this updating group type of simulation system group is actually the same as just not writing it because we're using this default simulation system group, but we'll get into that in just a second. The question then becomes, if every system lives in a system group, where do I then put those? Well, you put them in what's known as a world. So what is a world? A world is a group of systems and the entity data that those systems act upon. But then the question becomes, do I then also need to make a world in order to put the system groups in there so that I can put the systems in the system group? To which the answer is no. We will automatically create a world that finds all the systems that it needs and puts the systems in the correct system groups based on the attributes that you put. So if you don't put any attribute, it goes in the simulation system group, run every frame. Otherwise, it goes in the system group that you specified. Now, the question still becomes, how do I use the entity data? So far, we've just seen how we can write code, which is in systems. Earlier, I showed about moving across the screen, which is this piece of code. What we care about looking at now is the system API query part of it. I will quickly put it up to the right so I can explain what it means. When you create a system API query, what you're specifying here in this example is you're creating what's known as an entity query, specifically one that looks at local transform and speed. Now, what is an entity query? Well, it's a query that filters the world. So if we want to look for certain entities, like let's look at our bug, then let's see what this entity query matches. The local transform, it does match. The bug has local transform. It also has the speed component. And so, good. Our coder, however, doesn't have the speed component, and so it will not match. So if we look in our actual game, we can see the moving across the screen. What we will also see is that in this state of the game, we want one of the bugs to actually start attacking the coder. And so it should stop up and do that action. And that means getting the conflict state component. We consider that entity as being in conflict state when it's in front. However, now we want the query not to match certain criteria at some point. And so what can we do in that case? If we look at the data again, we can check the conflict state. And we want to make sure that the conflict state is not there, because if it were, that means that we are just about to hit something. And so we can specify that we don't want the conflict state component. That means it matches the bug we want and not the bug we don't want. The way we go about doing this is we add a with none function. The with none function allows us to specify a query that we can then loop over that doesn't include this conflict type. And so now the top bug moves and the bottom bug moves, but not the middle one. Now, where does this code then get run? We have one problem actually right now. System API query, while we have this 8-core CPU, actually only uses 1 core of the CPU. That's because it's main thread. Ideally, we want to be here when we're talking about entities. Ideally, entities makes it easy to go multi-threaded. So that's what iJob entity is about. iJob entity is similar to System API query, and so there's a direct equivalent for when you go to System API query into an iJob entity. It looks something like this. You create a partial struct, implementing iJob entity, and then you create an execute function, going and specifying which components you need. You'll also notice that you have to specify what's known as the read-write criteria. So in this case, we're specifying that we need the speed to be read-only, and we also want to read and write the local transform. We're doing this in the iJob entity case by specifying the ref keyword, and in the System API query case by specifying ref RW, standing for ref read-write, and ref RO, standing for ref read-only. We can also do the with none thing that we saw earlier. Now, obviously the question then becomes, why don't we put everything in jobs? And the simple answer is, not every problem that we come into actually can be thought of as like a multiple job problem. You have to sometimes run the main thread for some problems, like creating an entity. So how do I make an entity? We've currently been iterating over all the entities. Well, let's look at a bug again. We want to add some components to it, and we also want to create it. The way we go about doing so is we use what's known as the entity manager. The entity manager has a bunch of functions that lets us create, modify, and change entities. That's what it does. It's the entity manager. We can use the create entity function. The create entity function lets us create the bug, but the bug won't at this point have any components. So let's add a component. In this case, we are adding health. We can also set that component. We can set some health data. Now we can keep on repeating this, of course, for the rest of the components. At some point in our game, we want to instantiate this bug because we want multiple bugs. We don't just want one of them. And ideally, we don't have to recreate all that entity component data every single time. That's what instantiate does. Instantiate is just a mem copy, essentially. It's the fastest way that we can just copy data over to a new entity. And in our game, we want to create a bunch of them. But how would I normally do this in GameObject land if I want to, not have to create an object every time? Like normally in a GameObject, you don't create an object and then start adding all the components. You use a prefab. And you put a prefab in your folder, and then you open it up and start calling GameObject instantiate, passing in that prefab. So do we have an entity equivalent of a prefab? Yes. A prefab in entities is just an entity that contains the prefab component. So what does it mean to have this component? Well, the reason it acts like a prefab in this case is that, for one thing, having the prefab component means you no longer match queries by default. So all the code that you wrote earlier that moves a bug across the screen won't actually run on the prefab entity because it has the prefab component. However, it would run on the one that doesn't have the prefab component. Something else that also happens is that when you call entity manager instantiate, you will, on the prefab entity, it will actually get rid of the prefab component. And so now you have an entity that doesn't do anything, you call instantiate on it, and all of a sudden it starts doing stuff. There are also some pitfalls of what we just did. When we created the entity earlier, we did two things of what's known as structural changes. So what is a structural change? Well, when you're calling create entity will have to find somewhere in memory that is tightly packed for that specific set of components. In this case, when we created an entity, it had no components, so it finds a place in memory where all entities live that have no components. If we call add component data, all of a sudden we have to move that memory to somewhere new that actually has the space, or the shape of space, to call add component data. That means that there are some implication with structural changes. Because we're changing memory around, you can't have jobs running at the same time, because if those jobs were trying to access that data, of course, moving that memory from them now causes a race condition, right? So we have to stop all jobs. We have to create what's known as a sync point and stop all the jobs that are currently modifying data just to do a change with the entity manager. And so it can be quite expensive to do a structural change. So in your game, when you're making a game, you should try to minimize the amount of structural changes you do.
So one of the ways to do that is baking and authoring. Now, before I can explain how it solves our problem, I first have to explain what it is. Baking is the process of going from a game object in editor to an entity at runtime. Now, you can think game object in editor, all my game objects are going to become entities. No, only the game objects that are in what we call a subscene are going to end up as entities. Now, a subscene, very fancy word, is basically a normal scene that you add to an existing scene in a barely special way, actually, to notify us that we need to do the baking. So this does not happen when you enter play mode, though. What we do is when you make a change in your subscene, we bake it immediately and we serialize it to disk. And then when you enter play mode, we only deserialize. So when you're entering play mode, you're not waiting, we're not waiting, it's already there. But for the sake of today's presentation, you can just remember game objects in a subscene in editor to entities at runtime. So how do we do this? As I said, you add a subscene in a normal scene. So here you see code show is the scene, runtime is the subscene. Subscene add is just a game object with the subscene script on it. In the subscene script, you add your other scene, telling us this is the thing we want to bake. Everything in here, bake it. Well, how do we do that? Well, here the other part of the title comes in. We start with an authoring component. There we go. An authoring component, again, very fancy word. It's just a mono behavior. We call it an authoring component because this is how you let us know that this is the data you want to use during baking. The actual magic happens in the baker. In this case, the baker of the bug authoring. When you define a baker, you create a bake function. As you can see here, we're taking the authoring component, making sure that all the data that you defined before is available in your baker. So baking, game object to entity, right? So we're creating an entity and we're adding data again. But this is a structural change that we talked about. So to avoid this, you use the baking API. The baking API batches all the changes you want to do and does it at the end so that we have one structural change with all your components on it. To do that, you use the baking API. So instead of creating an entity, you get the entity that we are going to create for you at the end, and you add the component data again to the entity that we are going to create at the end. This means that when you're now adding all the components, this is not 5, 6 structural changes. This is one. We are batching everything. We're doing it at the end. So now we went from a game object with a bug authoring through a baker to an entity with all your components on it. Now, there's one thing that I haven't talked about yet, but is important, is again, prefabs. As you can see here, we're adding a prefab. But as you can see, we're not adding the game object prefab. We are adding the entity that was baked of the game object prefab. The thing this does is make sure that that prefab component that Daniel just talked about is automatically added. So now you have your game object, it's baked, prefab component added, and that is the thing we store on our component. And that's what you can use later to instantiate.
Okay, so if we were to type out this piece of code, specifically get entity, we would actually get a warning in both our editor and inside our IDE. Reason being that get entity actually needs to consider something called the transform and their usage flags. This code needs to look more something like this, specifying the transform usage flag. A transform usage flag specifies which kind of transforms we need of the entity. But what does that mean? How is transforms even represented in our game, especially in entities? Well, let's look at GameObjects first. Normally, when you have a transform, it does more than just specifying the world position. It actually specifies the local coordinates of itself, along with the world coordinates, the calculated end result of all its parenting, and also the parent relationship, both parenting and a quick way to get the children. In entities, we've split that data up so you can get the most minimal data you need in your case, because you don't always need all this data. For components, for the local coordinates, there's the local transform component. For the rendering matrix, so what actually is our world space position, that's the local to world. And for our parenting relationship, you specify a parent component with an entity as your parent. And then we also, from that, calculate a children buffer. To go a bit more into detail, say we had our bug in the game. We want to simulate it. The way that we normally would simulate something in our game is by using local transform. We don't need to, technically speaking, but it's what is being applied physics to. It's what you normally would do player movement to, so you can have children in the hierarchy. And when you want to then do rendering and have the smallest set for your rendering, that's where you use your local to world. The local to world is the minimal thing that you actually need to draw things on screen. And as a result, it's ideal for particle simulation, because a particle generally just needs that little thing that moves in space. And yeah, what you might notice also on screen right now is that we are moving local transform and then have an arrow pointing over to the local to world. That's because at some point in our frame, we're making sure that the local transform and its parent is turned into the local to world so that we can actually do rendering. That means that local transform doesn't really work without the local to world, but the local to world works on its own, and it happens at a certain point in the frame, which is the transform system group. But we won't dig into that right now. What we will dig into is the transform usage flags that we saw earlier. We had renderable, and renderable means that you just want for that entity to be drawn on the screen. So if all your mono behaviors are just saying renderable, then it will be drawn to the screen, and that's enough, and it will flatten the hierarchy. If there was something that said it needed dynamic in the hierarchy, then all of a sudden the whole hierarchy can't be flattened, and so it gets a parent component and the local transform for everything. If you then specified world space as your requirement, then you will force it to be flattened and have no parent component. But what the hell? This is very confusing. What does all these transform user flags mean? Do I need to care even? And the answer is, for the most part, not really. It's mostly for performance. You can, by default, just use transform user flag dynamic. It's the one that acts the most like a normal Unity engine transform. You get the parenting relationship. You get all the components that you think you would. So to recap, we've created entities. We can move them around on screen. We specifically created a bug that moves. But an important part of our game is the ability for our coder to shoot the enemy. And in most games, you would want for one object to be able to interact with another. So we need to talk about how to do entity interactions. If we look at this example of our projectile being able to hit our bug, we might remember from earlier that we had this thing called a conflict state that happened right before we hit at our target. This is what we're querying for here. We get a conflict state, and so we get all the projectiles that are about to hit something and all the bugs, but we specifically only do the ones that have no cooldown, because only our bugs hit over time. Our projectiles will just hit once. And so we know we're just getting projectiles. But okay, so we get the conflict state. We're looping over every projectile. We found the conflict state being the resolution of what's in front of us. And it, in this case, stores an entity in front of us. That means that we can now start asking questions about this entity. Like, for instance, does this entity in front of us have a health component? For this, we can use the system API has component. If we want to get the component of the health, say we have health in front of us, then we should check that we don't have any health. If we don't have any health left, then we should just skip it. Otherwise, we should try to apply some damage so that we can start, killing the thing. Something important to note is that we call system API get component, and that does a copy. So we are not actually modifying the data by just changing the target health. We need to assign it back to the actual underlying entity. And so for that, we use system API set component. We also want that projectile to then despawn. And for this, in this example, and in our game, we use a buffer, and we just enqueue it to be destroyed later. So we actually store the entity to be destroyed. We also make sure that if the target that we hit reaches below 0, then we should also kill it. So what we just did was we used system API. We might as well also have used the entity manager. Both of these are main thread only. So what do we then do if we wanted to work in jobs? Ideally, in entities, it's easy to turn your main thread code into job code. And so we have something called the component lookup. If we look at the example again, the system API query, we can modify it into this piece of code here, an iJob entity that specifies that it needs the conflict state and it needs damage, just like we saw before. In this case, we can still get the conflict state. It's totally fine for us to do in a job. What's not fine is using system API, so we can no longer do this. Instead, we need to use the component lookup. The component lookup specifies which component it is you want to look up information about. And then you can say, hey, does this have this component? That also means that the job now actually knows what kind of input it needs. Like, is it writing or reading to a health component? Is it writing or reading damage? That is something the job is aware of. We can also turn our get component and set component equivalents to the equivalent in component lookup. So that means that there's multiple considerations that we need to do when turning main thread code into multithreaded.
One of these considerations is job scheduling, or system and job scheduling, actually. Now, in what order does anything run? We generally care. So if we look at an example again, and we have three systems here. We have, three jobs. We have a spawn bug job. We have a spawn projectile job. And we have, once in a while, we have an update conflict state. Again, this is to make sure that when we're attacking, we update the conflict state so we're not moving, we're attacking and everything. So if you want to define these three jobs, you have a spawn bug job that takes a bug spawner, we have a spawn projectile job, and we have an update conflict stop. In this case, I've left the execute, the actual functionality of these functions away for brevity. Now, you might notice that none of these jobs interact. All of these three jobs can run in parallel. The only thing they have in common is the local transform, and that's read-only, so they can run next to each other, no problem. But you want an ordering. You want first your bugs and your projectiles to spawn before we go and look at our conflict state. So we put them in systems. Right now, Unity just does whatever with these systems. Job scheduling and system scheduling is actually really, really hard. So to make sure that Unity does it the right way, we can give it hints. In this case, we want the attack system to run after the spawn system. So we define an attribute update after. Of course, there's also an update before if you wish to reverse it or whatever. So now we have these two systems. Spawn system first, attack system second, and we've got the jobs within. But spawn bug and spawn projectile, in what order those run? You would like them to run in parallel, as you saw, they can. Right now, it's actually not the case, unfortunately. So under the hood, this code is actually rewritten to this. As I said, job scheduling is hard. So Unity tries to make sure that the dependencies are met. In this case, state dependency makes sure that whatever system needs to run before, whatever jobs need to finish before, are finished. And as you can see, the first job immediately writes back to it. which means that the second job now suddenly depends on the first job finishing. To do this, again, you can give hints. Instead of writing back to state dependency, you write back to a handle. Then you combine them, and only then do you write it back to state dependency, letting Unity and the job scheduler know, we know what we're doing, these can run in parallel, please do. So then we end up with the system we want. Spawn system first, attack system second, spawn job and spawn projectile job parallel.
Then the question becomes, how do I interact with the engine? Because a lot of the time when writing a game, you want to use what's already written for you, what's written in the engine. And you might want graphics, physics, netcode, even a character controller, and you don't want to write this yourself. There is a bit of a difference in the way that you write ECS code, especially from an API point of view. When you write a default game object, you're used to being able to get a component and then calling a function on that component in order to enact some sort of behavior on it. In ECS, it's still about getting the component. It's just instead you modify the data, and then some system at some point will pick it up and do the right thing. So the ordering matters. Now, this is the case for what we have already written. Sometimes there's still stuff we haven't written. And that means you need to go back to GameObjects. In the future, we're going to make GameObjects a lot easier. It's been talked about on the roadmap. We're making GameObjects entities so that you can take the full power of the entity component system and do this integration a lot easier. Right now, that's not the case. And so there's a few limitations. We don't have audio, we don't have animation, UI, or navigation. So, for instance, if you want a player with animation or an enemy with navigation, that's sort of difficult to model in our game, especially because you need some way of interacting from your entity, getting a reference to some game object, and doing a thing with it. So I'll try to go over an example. It's okay if you don't fully understand this part yet. We will give you some resources later. One approach to take when making game objects talk with entities is to create a prefab, a game object actual prefab, and then we sync that to an entity. So at runtime, we make sure to spawn the prefab entity, and then we sync the two together, changing so we actually have an entity that has references to the game object we created. The way that we can reference game objects on a component is using what's known as a Unity object ref. We haven't talked about Unity object ref yet. What they do is an ability for us to store a game object on our ECS component, and that means we can store a prefab. How do we then put the prefab onto our game object? Well, our component? Well, we create an author, like we saw earlier, and then we can add the component, specifically one where we add a game object prefab to our component, ECS component. And then at runtime, we go ahead and instantiate the game object. And because we've instantiated the game object at runtime, we now also have the actual game object reference to the newly spawned object. And so from there, we can then go ahead and get any sort of ECS component out of that, game object component out of that. And then we can store those on a new component added to the entity, making sure that we also go ahead and remove this game object to spawn so that we don't start spawning a bunch of game objects all of a sudden.
So now we've made it to the end. Hopefully we've made good on our promise and you now have a toolkit and an understanding of ECS and its APIs. But this is not the end. This is the start, basically. We have some further resources for you to look at. So first of all, the game that we showed you, the game that we used as an example, is online, and you can look at it, and you can go through all of it and look at the code exactly how we did it. Secondly, we've got the entity component samples, where each of the APIs that we've created within entities has its own example and its own explanation. There's also some great samples that are bigger, like the Metro City and the Galaxy game that you can look at. Think Metro City is outside here, you can look at it. Then there's also great YouTube videos by, for example, TurboMix Games and CodeMonkey And there's also a weekly show called the Hot Path Show, where there's different dots topics every week. So with that, we want to thank you for your attention and
Open up the floor for questions.
yeah, we're open for questions.
Yeah, so any questions? See one back there.
Hi there. You've mentioned simplifying converting game objects to entities in the future, basically combining them. But are there plans to simplify both systems and jobs? Because it feels to me like there are a lot of attributes right now, and system API querying is a bit clunky, in my opinion.
We are looking at stuff like that, yeah. But we can't go into detail right now on how we're going to do it. Any other questions?
Hello. You mentioned that game objects will have entities under the hood in the future. Does that mean that the entities will be also available in WebGL, for example, or WebGPU?
I mean, right now, entities is available in WebGL. WebGPU, I don't think it is. Don't quote me on that. As for like jobs, they are not supported because WebGL. But I know they are working on trying to get WebGPU working fully with entities. Entities graphics also doesn't work with entities right now. WebGL and entities graphics doesn't work together right now, so you have to create your own rendering implementation.
Mic incoming.
Quick question. Will using the entities improve the efficiency of the instruction cache as well as the state cache?
I mean, as far as the instruction caches goes, yes, in the sense that we have what's known as the burst compiler. That's not something we've mentioned during the talk, but the burst compiler does allow for vectorizing commands. It also allows for creating actual machine code, which is something the entities API is entirely built around to make it easy to use burst. And that means that we are optimizing the instruction cache because we're creating less commands. And as for the cache we just saw earlier.
Yeah. So with the back references to GameObjects from entities, essentially when you have the Unity object reference, sort of is there any pitfalls to the lifetime of GameObjects versus what you have in your components data in that case?
Could you restate the question?
So it's sort of like, given that you have a back reference to a GameObject, which is a managed object, right? And you have that sort of stored as a piece of data in sort of in the ECS data blobs. Is there any pitfalls to sort of lifetimes, given now that you have essentially a parallel world?
Yes. There is the fact that if you were to just do this and then not have what's known as a cleanup component, you need to make sure that you're also cleaning up the game object. Otherwise, you're just gonna destroy the entity, not the game object. And so this communication between like game objects and entities have different lifetimes. Ideally, if you destroy the game object, it also destroys the entity and vice versa. So I would generally recommend that you make sure that you implement in your game object some onDestroy that destroys the entity. So there's a back pointer to both sides that sort of make sure that they're destroying each other.
Yeah, and then sort of that is also tied to sort of that it needs to be imported in the sync points essentially, because you're doing essentially removal or sort of like some kind of structural change to your sort of your data set.
Yes, and now we didn't cover what's known as cleanup components, but cleanup components let you put it's a special type of component, and when it's on your entity, it means that when you go ahead and call destroy entity passing in an entity, then it won't destroy that actual component, and so you can store a back pointer to the game object. And now you did want to destroy the entity, So the last thing you have to do is query for an entity that doesn't contain a certain component that existed before, but does still contain that one cleanup component. And that cleanup component would then make sure that, hey, our query matches, I should now remove the game object that cleanup component is actually pointing to. That is sort of...
Yeah, so the process is really sort of like a two-phase commit process.
Yeah.
Where you stage the delete of it to get...
Yeah, exactly.
Yeah.
And you have it like at one point in your player loop.
Yeah.
You don't need to have like a bunch of asynchronous methods to do it.
Thank you for the presentation. My question is about the existing state of the ECS, because upcoming changes, they look like it's foundational or somewhat. So is it risky to start a new project on existing framework of ECS, or what kind of changes are we expecting?
So everything that we covered in the presentation should still be relevant for the things that we're talking about in the future. What's changing is just how easy this process in the last part of the slides will be. Like the GameObject entity interop will be a lot easier when you can just think of GameObjects as being entities.
Okay, so object reference component or variable will be simpler, or usage will be simpler. Yeah. Okay, thank you.
Yeah.
Hi. So my question is, there is a very simple way to usually debug game components, see the state they're in when you're working through them and prototyping. Is there a similar way or some suggestion on how to iterate and debug entity systems?
Generally, that's a tough question. So debugging ECS, generally speaking, means having to figure out, first and foremost, the data in your world. And the way to do that is just a bunch of debug logs most of the time. It's the easiest approach. You, of course, have the full ability to put in breakpoints and, yeah.
Okay,
I don't know. It's, there isn't a lot of tools other than we have some views that lets you inspect into how the world looks. So you can, like, there's a window for viewing components in the world. There's a window for viewing what's known as an archetype, which is a certain set of components. There's a view for viewing all the systems, and you can also disable certain systems in that view. Also, if you have the profiler on, it will view and give you a little memory span over time of like, these are the amount of chunks that were created, these were the amount of archetypes, and this is the fragmentation. You can see that in the profiler over time.
Alternatively, if you're debugging it, this is not as useful, but if you're trying to make testing or anything, systems take input and output basically data. So it's input data, output data. You have to make your own framework mostly, but you can use unit tests to basically give input and expect output, because it's simply a transformation on the data. So if you make correct unit test, you can check that the data transformation is correct. Of course, if you're debugging, this is not applicable, but if you're trying to make sure that your tests don't break or your systems don't break during the time, you can use this as well.
What are the benefits of using those compared to other CS tools like Leo CS?
So the question was,
What are the benefits of using those compared to other CS tools?
So this is more architecture stuff, more in theory. So I didn't cover this in the first start, but there's roughly two ways to implement ECS. There is sparse sets, and then there's archetype. Unity is built on archetype, and to not go too deeply in it, sparse sets is good when you're switching components on entities a lot. So for example, a UI system where you want to have an event system and you want to add and remove components all the time. And archetypes is good when you want fast performance in your game. So Unity is built, because it's mostly for games, it's built on archetypes. So there's a lot of performance while running systems. So it depends on which you want to compare it to, obviously. But if you're comparing it to a sparse set type like entity, that is a sparse set. It's just a different kind. So those are the two main reasons to use one or the other.
yeah. And there's also the fact that in our entity system, it's fully written for Burst, which is a particular Unity thing. And so it means that our API works more nicely with Burst than other APIs.
When should we care? Like, how do I know I have a game that has a certain performance issue like this? I know it's always better, right? But is the investment into like when should we optimize with the instance?
It depends on your game. There's two reasons one might use entities. It's one, performance, and it's also the type of game you're making is one where you might have a lot of different enemies with similar behavior, and so you want systems to play with each other. So it's also a way to design your game. The win in your game as a matter of performance is when you start lagging and you see a certain performance problem.
And how would you profile that specifically?
With the profiler, the built-in Unity profiler.
Okay.
Yeah.
It's about cache stuff, right? So does it go in CPU, memory? Like where do I see that you're expanding again?
Yeah, so right now there's various tools within Unity to look at performance, but unfortunately it's not that's where you look and that's your problem. Unfortunately, right now it is a bit of a intuitive thing. You have to at some point figure out, okay, I'm doing these many operations. You can see performance, like if you have a very heavy systems, that might be, very heavy on updates, that might be a reason to move to systems because you can parallelize it and then automatically you move to ECS. But for the data itself, it's very hard right now to figure it out. Also, unfortunately, you said, when do we care? Right now, you have to care when you start making your game but next generation, this would be easier. And then halfway you think, oh, wait, I'm actually running into problems. You can switch much easier. But right now, you have to actually care fairly early on.
Hey, in the start, you mentioned that the game objects have very fragmented memory and entities are very clean. So how does the interaction between when having a reference to a game object inside an entity and referencing its components, how does that impact the performance?
Yeah, it's not great. Unfortunately, right now it is what it is, but you're absolutely correct. It's not great. If you have a pointer, it first even has to resolve the pointer. So it gets the memory from the pointer, then it resolves the pointer, and then it has to wait again for the actual data to show up. So pointers not great. Pointers to game objects also not great. But you're absolutely correct.
But if you're dealing with game objects, it also doesn't matter because you're dealing with game objects, which are the slower equivalent.
And in the future version, when the interaction will be improved, are there any considerations to think about that, or?
I mean,
Is
the
there any way to
reason
improve?
we have these combination is for when ECS doesn't work or doesn't work yet. So it's not that we want you to use game objects because it's fast. It's that you cannot get around using game objects right now, and we're just making that easier until we can get more into ECS. And some things might not work ever, and then you have to use game objects. So we're not trying to make it easier for ECS people to start using game objects. It's for those who need it to make it easier for them.
You mentioned unit testing. I understand unit testing in edit mode jobs because it seems rather simple with structs. But how would you test systems, especially those which use system API? Sounds like we should use play mode tests only.
Not quite. So when writing unit tests, especially, it can be good to create your own worlds. So earlier I talked about what a world is, that it's a group of systems and entity data. It also means that you can create your own world and put in the systems that you want to test and then just call, hey, update this world, and then it updates all those systems. And so you will write that world to add all the entity data that you need, run the system, and then see what happens as a way of doing a basic unit test.
But
and that's available in the editor.
What about system API delta time or fixed delta time?
They are as far as you create a system and you just create a world and put that system in that world, then system API totally still works. system API works as long as you're inside a system.
But since I control the update loop, it calculates delta time from my input of update calls.
No, there you would also have to manually add the world time system, which is the system responsible for updating the time. Alternatively, you just modify the singleton component called world time, which is where the time in the world is stored for the delta time. So just manually update.
Okay, thank you.
Yes.
So in rendering objects, do you see a point in migrating halfways to ECS? Because I remember back then in 2021, the hybrid renderer came with quite a big overhead, and it didn't really make sense to have some game objects being rendered and some entities being rendered. So I'm just wondering what's the best way of migrating to ECS, or I mean, should I just go the old way? Is there a point of having both at the same time? Doesn't make sense performance-wise nowadays?
Do you want? No. So like when you create your game, ideally you first look at a like actual profile and see like where. But as far as like entities graphics today, it's certainly a lot easier than it used to be, just because you can register meshes and you can register what you need. I would probably decide to do my own testing. Like you should try to just see how much faster it is, because there has been performance gains in SRP in recent times on normal game objects. So you might see it be a lower difference today.
I mean, because I don't even want the rendering to be faster, just that the creation of the objects takes so long in the traditional system that I would like to use entities to create the objects, but then I would want to render them, of course, with whatever I need in ECS.
Yeah.
And then I have both renderings, the old objects and the entities. I just don't want it to be slower. So the creation would be faster with ECS?
Yes.
But then I don't want the rendering to be slower.
Oh, no. Well, the performance should be always faster in entities when it comes to graphics. Is that what you mean? Like.
Because I mean, if I render normal game objects and entities at the same, in the same scene,
Yeah.
then there was this hybrid render experiment.
Yes. Today we call it entities graphics.
Okay. And that doesn't come with an overhead?
Not really, no. So the way that we store rendering graphics is like every entity has a local to world, and then there is what's known as a render mesh, a mesh array info, something like that, and then a render mesh array. And then the mesh info just tells you, hey, which array should you go into, and then it renders them all in a batch. So it's all fully batched rendering, and so it's definitely a lot faster.
Okay, quick question. We saw systems using structs and implementing iSystem. I remember you could do that inheriting from system base and an abstract class in the past. Should we avoid using that one now?
Ideally,
30 seconds to answer.
Yeah. Ideally, where you can use iSystem because you have the ability to burst, but don't force it if you don't see a performance problem with it.
Thank you.
Unfortunately, that was it for today. Thank you all for coming.